Good afternoon, everybody, and welcome to this FIB Young Members Group webinar on strengthening of existing structures with high-performance cement composites. My name is Graham Webb, and I'm a member of the FIB Young Members Group Board, and I'm very pleased to be chairing this webinar today. For those of you who, or for anyone who is not aware, the FIB Young Members Group was started in, I think, 2017 as a way of encouraging some more younger people to get involved in FIB, as there was a little bit of a perception that you needed to be a kind of leading world expert in concrete to be involved in the work that FIB does. And so the purpose of this group was really to provide a platform for younger engineers to get involved, and some of the purposes of the group are to encourage the creation of national young members groups within each of the countries where FIB have national member groups, and getting more younger people involved in some of the FIB commissions and task groups. It's also a great platform for making and maintaining contacts, so promoting networking through different industries in different countries. The young members groups, both the international group and the national groups in each country, organise regular meetings, events, and things like site visits, which have probably been put on hold mostly at the moment due to coronavirus, but there's a wide range of different activities that the groups in different countries are doing, and we're also involved in things like the Best Paper Award competitions during FIB symposiums. If you'd like to find out more about what's going on, have a look at the International Young Members Group Facebook page, or there are pages on the main FIB website, or get in touch with your national member group, either the Young Members Group if there is one in your country, or the FIB National Members Group. Just a couple of housekeeping notes about this webinar. The webinar will be recorded and shared on the FIB social media channels. So if there's anything you want to rewatch, or if you've got any colleagues who would like to watch but have missed it, they will be able to find the webinar afterwards. All of the attendees are muted, so only the speaker and the panelists will be able to actually speak during the webinar. There are two features in Zoom for typing questions. There's a Q&A button, which should be available at the bottom of your screen. Please could you use that if you'd like to ask any questions. So type those into that box and we will try to answer questions at the end of the webinar. There's also a separate chat function where you can post things about sort of where you are and any sort of general feedback you've got. If you could please try and use the Q&A button for the questions. It just makes it a bit easier for us to keep track of them. So then I'm very pleased to introduce our speaker for today, which is Dr. Marta Del Zoppo from the University of Naples. She's also a visiting researcher at the Tokyo Institute of Technology and University College London. Marta's the chair of the FIB Italy Young Members Group, as well as being on the board of the International Young Members Group, and is involved in several FIB task groups. And she has interests around seismic assessment and kind of seismic retrofit engineering. And so I'm going to hand over to her to give her talk about strengthening of existing structures with high-performance cement composites. So Marta, over to you.
Thank you, Ram. Hello, good afternoon. Hope you can hear me and see the screen properly. So, good afternoon, and thank you for being here today. So, many thanks, first of all, to the FIB for this opportunity that is given to young researchers to expose and talk about their work. And today, I will discuss with you about the potential of using high-performance cement composites for the strengthening of existing reinforced concrete structures. So this is the structure of the webinar. We will start with a brief introduction about the needs of existing reinforced concrete structures, and the presentations for definition of high-performance cement composites and their mechanical properties, and then we will see some typical applications of such materials for the strengthening of structures, and then we'll do a focus on the seismic strengthening and seismic performance of columns. With this kind of strengthening solution, then we will see a comparison of this new technique with the consolidated jacketing with fiber reinforced polymers, and then we will see the conclusions. And okay. So nowadays, let's start with why we want to strengthen existing structures. So the topic about strengthening is quite okay. So I see there's a problem with the volume. Okay, maybe you can now hear me better. I will raise my voice a bit. Okay, so I was saying why we want to strengthen existing structures. So nowadays, one of the hot topics is about sustainability and reduction of the carbon footprint in the construction sector. And we try to find new solutions for the design of new buildings, which are more efficient and sustainable. But of course, we need to consider that most of our structures are actually existing. We have more than 90% of the structures are existing, and just 1% is the new build construction. So, of course, we need to maximize the use of such existing structures, so building less and maximizing the use. Of course, when we deal with existing assets, we need to consider that they suffer of deterioration problems, and they usually do not comply with current standards for design. So of course, we need to design proper retrofit and strengthening intervention of these structures that should not only ensure an adequate safety level for the structure, but also increase the service life of the asset. We have currently in this field several well-consolidated techniques for the structural strengthening of existing assets, of course using traditional materials and innovative ones like the fiber reinforced polymers that of course now can be considered as a consolidated approach for the strengthening of structures, but we have also several new materials and composites with improved performance that can be considered as emerging alternative and more efficient strengthening solution for the structures. Today, we are looking at a class of recently relatively new materials that are classified as high-performance cement composites. These materials are characterized by high compressive strength, up to 150 megapascal in compression. And of course, this increase in compressive strength is as a drawback, that is the brittleness of this material. So to contrast this brittle behavior, we can add fibers, so short or long discontinuous fibers inside this material can improve the tensile behavior of the material itself. And this kind of material is called fibre reinforced cement or cementitious composites. So fibre reinforced cement composites are characterized by very low water to binder ratio and very small or fine aggregates, and also the addition of these discontinuous and randomly distributed fibers that can have different aspect ratios, geometries, and also material. But the most important thing is that these fibers should have a high tensile strength and also a high resistance to corrosion in order to improve the durability of this composite system. So looking at the general properties of such materials, we can say that thanks to the effect of the fibers embedded inside the matrix, we have a high tensile capacity, as we have said before, but we have also high fracture resistance, since the fibers allow to control the crack formation and propagation inside the material during the load condition. Then, given the low water to binder ratio, such materials have a very, very low porosity and shrinkage, and so they can ensure a high durability and also a carbonation suppressing effects when applied to existing structures. And finally, they have an improved residual capacity under high temperatures, so for fire exposure, and also a high toughness that can ensure good resistance against impact loads. And last but not least, these materials are self-compacting in the first state, and so they can be poured in very narrow gaps, allowing so to be applied on structures in very, very thin layers. And this is a very good and important characteristic when we deal with the strengthening applications. So these fiber reinforced cement composites are actually classified based on their tensile behavior. And their tensile behavior strictly depends on the fiber's volumetric ratio inside the matrix. So if the volumetric ratio is lower than 2% in our material, we will have strain softening behavior in tension. So this is the behavior. So after the achievement of the peak capacity, the peak tensile capacity, we will have the development of a first microcrack in the matrix, and then a sudden loss of capacity and a residual tensile strain, tensile stress that is caused by the bridging of the fibers inside the matrix. This behavior is called strain softening because after the peak we have a reduction of tensile capacity, and this is typical of the materials called ordinary fiber reinforced cement composites, which is very similar to fiber reinforced concrete. But when the volumetric ratio of fibers is higher than 2%, so in this case, we will have a different approach. So under tensile strength, during the tensile test, we will have the development of multiple macro cracks, like shown in this picture. So differently from the previous case, we will have multiple airline cracks and a strain hardening behavior. So after the achievement of the first crack, we will have an increasing tensile capacity until the achievement of the maximum tensile capacity of the material, and then we will have again the strain softening behavior up to the failure. In this case, we have these materials are called strain hardening, and they are classified as high performance fiber reinforced composite cementitious composites. So ordinary and high performance fiber reinforced cement composites are currently applied for the repair and strengthening of structures, even though up to date we don't have any guideline that regulates the design and application for such kind of strengthening solution. And the most typical applications are under ordinary load conditions, mainly consisting the retrofit of the bridge decks. In particular, we can do an overlay of the high performance fiber reinforced cement composites over the decks of the bridge, and this is adopted to mitigate the deterioration of the bridges under aggressive salt attacks, and also to improve the durability, of course, of the decks. Such kind of materials are also commonly applied as a surface repair, so without any structural effect, so just to protect the deteriorated concrete surface, because of course we have this high durability of materials. So basically, this kind of approach are used for structures in aggressive environments like cold regions, offshore structures, and also dams or whatever. But they are also used for as a protection, surface repair in the case of to preventing fatigue cracks, because of course we have a higher crack control. So in structures like viaduct or bridges, we can control the cracks thanks to this advanced control given by the fibers inside the matrix. And for structural applications, mainly for buildings, we can find application on slabs where we can adopt an overlay of fiber reinforced cement composites on the top of the slab to increase the flexural and shear capacity of the slab itself. But we can also have application on the beams and application on the columns. In the case of the beams, we can increase both flexure and shear capacity thanks to the application at the bottom of the beams or on the three sides, like a U-wrap of the beam with this additional fiber reinforced cement composite jacket. Or in the case of columns, adopting a full jacketing of the member with this new material, we can increase the axial load capacity thanks to the confinement. The adoption of such materials for the seismic strengthening is still under investigation, and only a few examples of this can be found up to date in literature. When we talk about seismic strengthening, we need to first understand which are the main deficiencies of our existing assets. Well, existing structures are often designed according to very obsolete seismic design codes, or sometimes also for gravity loads only, and usually exhibit very poor performances during earthquakes. So the main issues of these kind of structures are related to the lack of details. So in general, we have the lack of transverse reinforcement inside the beam joint panels. So we don't have stirrups inside the joints. The lack of stirrups or transverse reinforcement in columns and shear walls, and then other design issues related to a wrong strand hierarchy between beam and columns, but also between flexure and shear. And for buildings that are built before the 70s, usually we have also the adoption of bars with so smooth bars, which lap spliced region, and also very poor quality concrete because the quality of materials was lacking at the time. So often we have concrete with very, very poor compressive strength. So FRCC and high-performance FRCC can be adopted as seismic strengthening solution in terms of jacketing for the beam column joints. So we can apply an overlay of this FRCC or high-performance FRCC on the panel, on the joint panel, to increase the shear capacity of the joint. Or in the form of jacketing for columns and shear walls. And this jacketing can involve the full length of the specimen or just be localized at the bottom, for example, in the case we are dealing with the plastic intervention on the plastic hinge region or for the lap splice region. But in general, we can say that this kind of strengthening solution is suitable for structures that are characterized by a very low quality concrete and also some deficiencies like low reinforcement ratio, lap spliced bars, and also in the case of deterioration. So when we have other problems related to the corrosion of the members. Let's now see how the jacketing with the FRCC actually works. So first of all, we need to understand which is the actual condition of the asset that we want to strengthen. If the substrate of the assets of the member that we want to strengthen is in good condition, so in this case we can apply the jacket over the existing cover, original concrete cover, and so in this way we are doing a sort of cross-section enlargement of the element. So of course, first of all, we need to clean the surface and repair if there are, for example, cracks, airline cracks with epoxy injection or mortars. And we need to increase the roughness of the surface because we need to ensure a good bond between the existing concrete cover and the new material and the jacket. So we need to sandblast the surface or increase the roughness with hammer jacks or other methods, and then we can apply our jacket with different kind of materials and can be taxotropic, sprayable, also prefabricated panels. The point is that this kind of materials works well when applied with very thin layers. So basically, this jacket can have a limited thickness, usually less than 40 millimeters. So even though if we are doing a cross-section enlargement, actually, this is really negligible with respect to other kind of application, like for example, the traditional reinforced concrete jacketing, where we are dealing with very massive cross-section enlargements. The other option is in the case of structures that are already deteriorated, and usually this is also the most common condition that we have in our countries due to the lack of maintenance. Usually our structures are very deteriorated with the concrete cover crack or detached and corrosion of the bars. So in such a case, the alternative is to replace completely the original cover with a new one made with this FRCC. So basically we are creating an high performance cover for the member. So the first step is to, in this case, remove completely the cover and of course clean the bar if we have corrosion. Then we need to repair the member if needed. If there are cracks, we need to do some epoxy resin injection. But of course, we don't need to increase the roughness, because thanks to the removal of the concrete cover, the surface will be rough enough to ensure a good bond between the jacket and the original member. And then we can apply the new concrete cover. In this case, so the enlargement, the cross-section enlargement is really null or negligible, because the jacket will replace completely the original cover. If you want to use also the tensile capacity of the jacket, so of the FRCC, for increasing the flexural capacity of the member that we are strengthening, so the jacket needs to be, of course, anchored to the foundation or the footing. Otherwise, the tensile zone will be not collaborating in the bending moment resisting mechanism. So different solutions have been investigated so far. One consists in creating a pocket inside the footing. So this pocket will be filled by the FRCC during the casting or during the application, creating a solidal jacket between the element and the foundation. The other option is to add an additional new light longitudinal reinforcement just in the critical zone of the member to guarantee the connection between the footing and the jacket. But in this case, of course, we need to consider that the thickness of the jacket is really small. So to avoid corrosion issues, we need to select a material and also diameter for these bars that should be able to avoid durability problems and the corrosion of the bars. In any case, of course, when we increase the flexural capacity of the members, we also need to ensure that the correct hierarchy between the shear and the bending is respected. Otherwise, we are creating a new problem, creating a shear critical member. So when we adopt flexural, when we connect the jacket with the foundation, we need to pay attention at the shear capacity too. So after this general overview about the use of fibre reinforced cementitious composites as a strengthening technique, we will now see in detail how the jacketed columns will perform during seismic actions. So for this application, I'm adopting 30mm thick layer of fibre reinforced cement composite with a strain softening behavior. And this material is applied for the full length of the columns in replacement of the original cover. So with a very slight cross-section enlargement. The columns that we are analyzing are made with a poor quality concrete with an average compressive strength of about 15 megapascal. So these are the mechanical properties of the FRCC that we are adopting for this application. So as I said, we have a high performance in compression. So we have a compressive strength of about 120 megapascal. And in tension, we have a peak strength of about 4 megapascal. And then we have this strain softening behavior. With the residual tensile strength that is given by this bridging effect between the fibers. For this material, we have low volume ratio fibers, that is less than 1%, and short. We are dealing with short plane fibers with length less than 20 millimeters. And now we will see the potential of using such jacketing technique for improving the performance of flexural and shear critical columns, and also for the retrofit of columns that are, have already experienced an earthquake and are likely damaged by after this event. To assess the seismic performance of the jacket columns, we perform full-scale quasi-static tests with this setup and load protocol, so cyclic lateral loading. And the behavior of the jacket has been monitored during the test by means of the digital image correlation. That is a technique that allows to track the behavior of the behavior and the strain distribution during the test on the jacket. So this is the first application, and this is on a slender column that is governed by a flexural failure mode. So during the test, the column developed flexural behavior, so achieved the maximum bending capacity, and then showed a sudden drop in the lateral strength caused by this shear flexure interaction. So of course, this shear interaction limited the ductility of the specimen. And the same specimen, without any damage, has been strengthened with the technique that I discussed previously. And of course, in this case, we are slightly increasing the cross-section from 300 to 320 millimeters. And we are not adopting any kind of anchorage system between the jacket and the foundation because we don't want to increase the flexural capacity of the specimen, but just to look at the possible increase in ductility. So this is the behavior of this specimen during the test. So basically, looking at the strength field during the digital image correlation, thanks to the digital image correlation, we can see how the strain fields are changing during the test on the jacket and how the tensile concentration, tensile strain concentration are localized near the cracks in the jacket. So we can still observe this macro cracking behavior of the jacket, of the FRCC material. And also we can note that a large gap is opening at the bottom of the specimen. So at the interface between the jacket and the foundation block. Okay, this large gap opening at the base of the specimen suggested that the behavior of the jacket columns was actually behaving like rigid body more than like a flexural element. So developing a rocking with respect to the base of the element at the base section. So to further understand the overall performance of the jacket columns, we perform a curvature analysis starting from the edit records. So basically, the digital image correlation is able to provide a picture of the strain over the surface of the element at each instant of time. So basically, from these strain values, we can define the cross-section curvatures at any step of the test, and then define how these cross-section curvatures are changing over the length of the specimen for each imposed displacement or drift. So this is the plot of the cross-section curvature over the height of the specimen during the test for these different imposed drift ratios. And we can see it is clearly visible that the curvatures in the potential plastic hinge regions are almost zero. That is meaning that the flexural deformation are almost negligible for such column, and that all the deformations are actually concentrated at the base interface in the forms of base rotations. And these peaks that we are observing in the plot are actually false curvature peaks that correspond to the opening of the jacket that we observed during the test, the opening of the cracks in the jacket. So basically, they are rigid rotation around the crack developed in the jacket. So basically, this is important when we need to model the behavior of such element, that we need to consider that all the assumptions that we usually do about the plastic hinge approach are not valid for such kind of elements, but needs to be further investigated. And this is the failure mode of the jacket. So up to a certain level of deformation, we achieve the crushing of the jacket with a sudden loss in lateral capacity that is basically related to the strain softening nature of this material. So when we have a crack in the jacket, that it will be open very fastly after the bridging of the fibers. However, the jacket was able to prevent the shear flexure interaction that we observe in the bare column, and also increase significantly the ductility of the element. Then the second application is about the shear critical columns. So in this case, we have another specimen that is that exhibit a very brittle behavior during the cyclic test with a poor ductility performance and without achieving, of course, the yielding of the rebars. And these are the classical diagonal cracks developed on the specimen due to the shear. And now let's see also for this case, which is the behavior of the jacketed specimen. Also looking at the records from the dig, so the strain fields, where the yellow are the tensile strains concentrated where the cracks are developing. So we can still see since the beginning this rocking behavior around the base of the column, the foundation interface, the opening of the first flexural cracks, so flexural behavior until now. Then we have the first opening of the diagonal crack due to shear. The fibers are working to bridge the crack, so to close that crack, until we have the final opening of the jacket caused by the shear. So if you look more in detail about the failure mode and the shear crack, we can see how the fibers that are crossing the crack are trying to bridge the two edges of the crack until we have the complete debonding of the fibers. Of course, we are working with short fibers, 20 millimeters, less than 20 millimeters length. So when we have the complete debonding of the fibers, we have the complete opening of the jacket. And in terms of performance, if we compare the capacity curves, we can see that the jacket allowed the achievement of the flexural capacity, and so a ductile behavior for the specimen. And also in this case, of course, when we have the opening of the jacket, we observe a sudden loss of capacity. And this is clearly given by the nature of this material, which is strain softening. So this is related to the kind of material that we are using for this test. And this is just to compare how the behavior of the specimen changed, just replacing the original cover with a new one made with Fibre Reinforced Cement Composites with FRCC. So we completely changed the failure mode, increased the activity of the specimen. And finally, the last application is to show how the jacket can modify the performance of seismically damaged members. So in this case, the same flexural columns that we have seen for the first application has been pre-damaged with this input. So basically, we achieved a 3.2% of drift. And then we applied the jacket. So basically we repaired the specimen because of course it was damaged. So we removed the concrete cover, we repaired the cracks with the epoxy resin injection, and then we cast the jacket. In this case, we also consider possible anchorage systems to recover and try to increase also a bit the flexural capacity. We create a pocket inside the foundation block as visible in this picture, and so we cast the jacket in order to have a higher bonding surface between the jacket and the foundation. And this is the behavior of the retrofitted column. So if we look at the capacity curve, we had a full recovery of the original capacity and also a slight increase in flexural strength, full recovery of lateral stiffness, and also good ductility. But if we look at the failure mode, given this anchorage system adopted for this kind of test, we observe this the formation of cracks inside the foundation, and then the creation of this sliding surface inside the foundation, which is an undesired actually failure mode. So basically, other anchorage systems need to be considered if we want to try to apply and to adopt the flexural strengthening for these techniques. But in general, if we compare the behavior of the specimen, so the damaged and retrofitted specimen with the behavior of the bare one, so the original one without any damage, we can see that we have a very, very good result in terms of recovery of the original capacity, and also we are avoiding the flexural shear interaction that we observed in the original specimen that limited the ductility. So until now, we have seen and also understood how these materials behave when used as jacketing for members under seismic actions. And now we can see some comparison between this new jacketing technique and a more consolidated one that consists in the use of fibre reinforced polymers jackets for the members. So in this case, we are comparing for the flexural column, so the first application that we have seen, with the same column, in this case, jacketed just at the plastic hinge region with one ply of carbon fiber reinforced polymer with unit weight 600 grams per square meter. And if we look at the comparison of the behavior, we will see a bit difference between the two performance curves. So basically, when we deal with fiber reinforced polymers, of course, we don't have any increase in lateral stiffness, any increase in flexural capacity, because we are just applying a confinement, a passive confinement for the member. But we are preventing any kind of sudden failure modes that can reduce the ductility of the specimen, and we allow a very softening branch. While in the case of the FRCC jackets, we have this slight increase in lateral stiffness. In this case, we have also a slight increase in flexural capacity, and this is related to, of course, the slight cross-section enlargement that we are doing when we apply such kind of strengthening solution. And we have this increasing behavior until the sudden failure of the jacket. So if you want to have more deformation capacity and some more ductility, we need to probably adopt longer fibers to avoid the sudden failure after the opening of the jacket, or the adoption or adopt additional mesh reinforcement to use such a system as a confinement technique. And this is the case of shear critical columns. So in this case, we are looking at the application 2. So shear critical column first jacketed with the FRCC. And in the second case, we have discontinuous jacketing with steel carbon FRP, same unit weight of the previous case, so 600 grams per square meter. And these strips have a wide 100 millimeter dimension and spaced at 165 millimeters. And this is the comparison between the two specimens strengthened with the two different strengthening technique, of course, always in comparison with the bare behavior, that is the red one. So we can see that both the systems are able to increase the flexural capacity, the capacity of the specimen, so avoiding the shear behavior and allowing the achievement of the flexural capacity of the member. So in both of them, we are achieving the flexural yielding. And then after that, of course, the FRP, thanks to the longer fibers, so we have these continuous long fibers in the transverse direction. Also in this case, the FRP allows a very gentle softening behavior, while in the case of the FRCC, up to a certain level of deformation, we still achieve the failure of the jacket, and the opening of the jacket, and so a sudden loss of lateral capacity, also in this case. But still, we can say that comparing the two systems, the FRCC seems to have a high potential and to be a valid alternative with respect to FRP systems, and also providing additional benefits such as the increase in the durability, in the fire capacity, the fire resistance, and also resistance to impact loading. So just to conclude, we have seen that the strengthening with high-performance cement composite has a high potential for increasing the structural performance and also the durability of our existing assets. So they can be used just not only for the surface repairing, but also for structural meaning. The adoption of such strengthening solution for shear critical members is highly promising because it allows the change in failure mode. So with just the replacing of the concrete with a new high performance one, we can, in some cases, of course, depending on the column, we can change the failure mode from brittle to ductile one. These kind of systems can also be used to restore and recover the capacity of likely seismically damaged members, also increasing the capacity if an anchorage system, a proper anchorage system is adopted. But the point is that this kind of jacket is changing the behavior of the members. So we are not dealing more con flexural members that develops flexural deformation, but we still have a deformation at the base of the member in terms of base rotation and a sort of rigid rocking behavior of the entire member itself. When we deal with small thickness, we need to pay attention because of sometimes really small asymmetries in the jacket can lead to a very different behavior in the positive and negative direction of the members. So a very much attention should be paid when during the application of such materials. And of course, the short length of the fibers and the strange softening behavior prevent the achievement of large deformation. So we cannot achieve very large ductility for these kind of specimens. And of course, much more work needs to be done to allow the regulation and standardization of this technique to be used for the design of new strengthening solutions. And thank you for your attention. And this is my contacts if you need. And I want to thank also my co-authors and supervisor for this work that has been done as partial part of my PhD dissertation.
Thanks very much, Marta. If anybody has any questions, please could you type them into the question panel? Would you like me to read out questions that come in, or do you want to look through them, Marta?
Yes, I can see in the Q&A. There's a question from Vlad. Oh, there are three actually. Question from Vlad. Okay. So what is the time between making a compound and hardening? The maximum time to perform jacketing? I'm not sure about this question. What do you mean? Okay, of course, the hardening is quite fast for this kind of material. If I well understand the question, the hardening is quite fast for this kind of material, so we need to cast it quite quickly. So, and also the application by hand should be done quite quickly. And then we have this fast hardening of the material. And can workers make this mixture on construction site? If not, how it can get there? If there are any feature in delivering? So basically, the application of such solution like the FRPs is for specialized handwork workers. So basically, usually people from the company, if we deal with commercial materials, there will be a person from the company that we go to the site and do the mixture and also apply, help with the application, at least at the first, for explaining how these kind of systems need to be applied on site. And usually the delivering is in the form of two components. So usually we have the two different sets for the matrix and the fibers that need to be need to be mixed on site usually. But of course it depends on the company that is providing the material. What about the workability? If we have a low water cement ratio, do we need vibration? So the best part of this material is that since it is self-compacting, actually we don't need any vibration. So we just need to mix the two with the water, of course, and then we can apply it on very small layers. So we cannot vibrate the material, so we just apply it as it is. It doesn't need any vibration. Okay.
Note there's also a question from Jean-Nicolas in the chat who's asked us, or perhaps a comment, that it looks like the strain obtained is very high for the strain softening behavior, and was the scale right?
So if we look at the tensile behavior, yes, actually, yes, the plot is, the scale is right. And yes, we achieve very, very high tensile strains. Of course, with a very residual, so very small tensile strength, because we have this effect of the bridging. So actually, this is not a real strain in the material. You need to think that actually it is the effect of the fibers that are crossing the crack. So basically, so the matrix is cracked, but the fibers crossing the crack are still working and are ensuring this deformation. So yeah, this is the main advantage of this kind of materials, is high rate of deformation. Okay. Perfect.
I was also wondering, how does the cost of a strengthening like this compare to other techniques like the sort of FRP jacketing that you were comparing it to?
Yes, it's almost the same. That's why I'm also comparing these two techniques, because basically the cost is almost the same, but this system can be applied very fastly. So basically, after the first induction from the company on how to create the mixture and how to apply it, actually it should be just cast or apply by hand. So also a normal worker can do it after just a bit of induction. And so we are reducing not just the cost of the material is almost the same, but we are reducing the cost of the specialized hand workers, because a normal one can do it after a bit of induction. That's the big part. Thank you.
We've got another question from Vlad. How long does it take to get to the design characteristics of the material?
How long does it take? Okay, basically, it is a concrete. I mean, it can be treated as like a mortar, actually, but still, I think we need to wait until 28 days, like for normal concretes, for having the full behavior of the full capacity expected for this kind of material. So usually we test it at 28 days, like for normal concretes. Okay.
And I got one more then. I was also wondering, do you need to look at the shear between your new layer you apply and the existing column? So if you had something in Flexure, you could end up with a shear failure on that interface, or does that not end up governing?
Well, we don't have any failure at the interface because we have a very good bond between the material and the original concrete cover, or the original concrete in general. So basically, if we have failure, when we have the flexural behavior, we don't have any kind of failure at the interface, so governed by shear or loss of bond.
Okay.
Okay.
If anyone's got any last questions they can think of, please do type them in. Otherwise, it looks like you've answered everything.
Okay, so thank you very much to all of you for the interesting questions.
Thank you very much for the interesting presentation. And also, I just like to note there's a few upcoming webinars which will be appearing on the FIB website very soon to sign up for. The next one is on the 29th of October, where Andri Setiowan is going to be talking about an efficient strategy for modeling punching failure of flat slabs. Then we've got one on the 4th of November, which will be Muslim Shavardi from EMPA, looking at the development and application of an iron-based shape memory alloy. And then on 3rd of December, we've got about one per month, with Leonardo Todisco from Spain, talking about post-tensioning for structural innovation. So look out for those, and thank you once again to Marta for a very interesting presentation, and thank you everybody for joining.